The previous section showed how to solve a problem if we have some number and we have x squared on the top and we have a number minus x squared on the bottom, and we call this simple square root. Well, if we don't have that kind of mathematical situation, what we're going to do is we're going to use the quadratic equation. To refresh your memory, the quadratic is ax squared plus bx plus c equals 0. And in order to solve for the x, you use this formula. So what I have here is an example. Let's say we have 0.6 moles of A and 0.2 moles of B. Notice they are different numbers. If we put them in a container and let them reach equilibrium, what is going to be the equilibrium concentration? And again, I note here, A and B initial are different. So I set this up before I came to make this video, and I did the exact same thing I did for the simple square root. I took my made all my initial concentrations by looking at moles per liter. I then put them into an ice table. Now what we're going to do on the next slide is start using the x's. The point I want to make is we have the exact same change line as we did for the simple square root. We have kind of the exact same equilibrium line. The only difference now is we have different values for the reactants. So what's going to happen here? Well, we're going to set it up the same way. We're going to say 49 is equal to x times x. We're going to divide that by 0.300 minus x multiplied 0.100 minus x. We cannot take a square root here. So I worked each and every detail out. 49 is equal to x squared divided by 0.300 minus 0.400x plus x squared. You're probably thinking, where am I going to use this? Well, when we do weak acid calculations, we're trying to find a pH. If we have a Ka that is a difference in value of more than 1,000 from the initial concentration, this is the method that you have to use. So what you come up with is 49 times 0.300 minus 0.400x plus x squared equals x squared. And I used another slide so that I can work this out a little bit further, okay? So this comes out to be 48x squared minus 19.6x plus 1.47 equals 0. There's my A, there's my B, and here is my C. So I'll substitute that into the formula. X is equal to a negative 19.6 plus or minus the square root of minus 19.6 times 2 minus 4 times 48 times 1.47, and I need to take the square root. I will divide that total numerator by 2 times 48.0. Again, refer back to the slide to see how I've done the substitution. X is going to be equal to 19.6 plus or minus the square root of 1/2. Now, when I solve for x, I get two answers, 0.309 and 0.99. Only one of these roots has a physical meaning. When you look at 0.309, that's greater than the 0.300 molar that we started with, so that cannot be a root. This is actually the root and the value for x for this problem. So I wrote it down here again. Here we have our two different values. The quadratic always yields two roots. One root has a physical meaning. The other root, it's mathematically correct, but they say it's extraneous. It has no physical meaning whatsoever. No more B can be consumed that was initially present. So x equals 0.3009 is going to be an extraneous root. And Here are going to be our equilibrium concentrations. We will say 0.300 minus x, which is 0.300 minus 0.099. That's going to give us a value of 0.201 molar. For our B, it will be 0.100 minus x 0.099, and that's going to give us a very small number, 0.001 molar. For both C and D, we're going to have 0.0999 molar. So we can check this by looking at Q. It'll be C times D divided by A times B, and we plug in our values, 0.099, 0.099. We divide by 0.201 times 0.001, and we come up again with the number equal to 49. So two different methods are used to determine the x value in one of these equilibrium expressions. As I mentioned in chapter 16, acid-base chemistry, we're going to then use that x to help us determine the pH of a solution, and this is primarily when we have weak acids. So to wrap things up, textbook versus reality, we're giving you the basic fundamentals of equilibrium. We know that when they make ammonia, they could measure different Ks depending on temperature. What they did when they did their experimental design is to look at total pressure versus temperature to find out how much ammonia was made. That's kind of what we don't even go that far. But when you look at how an industrial plant functions, the engineers engineer the system, and it is pretty complicated. And this is a real industry, $28 billion. So your job really is to understand what an equilibrium constant is. It's products over reactants. If they give you all the values, you just calculate it. If they don't, you now know two different methods involving the variable x in order to come up with an equilibrium concentration.